Welcome everyone. We just heard an excellent ITC colloquium by a former ITC member, Elena, who is an assistant professor. And she will tell us more. She's from Madison, and she will tell us more in a few minutes. We'll have 5 presentations. The first one will be very brief. It's an update on a topic we discussed before. And it will be given by Peter Williams in work that he did with Neil Berger on the claimed localization of the fast radio burst, which apparently was not real, as Peter will tell us. And then we'll hear from James Guillochon from the ITC, our own, who will talk about an open catalog for supernovae. So James is a theorist, but this talk will demonstrate that theories are also useful for observers. And after that, we'll hear from Elena and that will tell us about tidally-induced offset disks in Magellanic spiral galaxies. And finally, we'll hear from, we'll also hear from Rychard Bouwens, who is visiting us from Leiden. And he will tell us about the successful identification of the highest redshift Lyman-alpha emitting galaxies. And finally, we'll hear from the CFA colloquium speaker of today, Rychard Kremer, who is sitting somewhere over there. He's visiting us from Dartmouth, and he will talk about Charles A. Young, Alvan Clark, and the early American astrophysics before the diffraction grating. And I would like to advertise the fact that Owen Gingrich is taking Rychard for dinner tonight, and anyone that would like to join, please contact Owen. He's sitting just 2 seats away from me. Peter.
Okay, thank you, and thanks, Avi and the organizers for squeezing me in. Hopefully, I will try not to take up too much of your time. So as Avi described, this is an update on this thing that we talked about a month ago, where the superb collaboration claimed to have obtained a precise localization, the first precise localization of a fast radio burst. The way they did this is they saw this fast radio burst, which is a millisecond timescale pulse, and they observed, so the top panel up here is approximately the size of the overall localization precision, and they observed this with a higher resolution radio telescope and saw a radio transient that they claimed, so a radio source that was brighter than faded, that they associated with a fast radio burst. And that transient was weak timescale, so much longer than the burst itself. The localization of that transient, it maps to a host galaxy at a redshift of about 1/2, which would be really exciting because that would imply that FRBs are cosmological, which means that, first of all, they're incredibly bright. We have to understand where they're coming from. And also that means that through their dispersion through the IGM, you can probe the IGM structure in a way that we really aren't able to do right now. And so, many elements of this thing are fine. The FRB is definitely a real event. The variable radio emission that they observed is definitely variable, and it is well localized to this host galaxy, and the redshift is fine. So all those pieces are okay. But this does, depend critically on the association between the FRB and this longer time scale radio variability. And that has some problems. So first of all, these are showing the data in the original paper with some models. I'll talk about the models in a second. So there's 5 red points, 5 black points are detections at 5 gigahertz. And then there's an upper limit and detection and 4 upper limits in red. Those are 7 gigahertz. So I would like to say, if you're looking at any kind of variable object, the fact that there's no pre-outburst imaging, if you can call it that, and you sort of have 2 up measurements and 3 down measurements. That is vaguely consistent with a transient, but it's also consistent with a lot of other things. In particular, if you do think about radio transients that we know from extragalactic sources like GRBs, they have a very characteristic sort of evolution. They're kind of synchrotron fireballs. So these log scales, these solid lines here are sorts of models that fit to these things. And they really don't fit the data. In particular, right between 6 and 8 days, the 5 gigahertz emission drops very abruptly, and there's a very strong spectral evolution. And you just don't see those in these synchrotron models. Finally, The other worrisome thing is that the luminosity implied by this kind of quiescent type emission is large enough where pretty much it has to be due to an active galactic nucleus because star formation in this galaxy is ruled out to a high level. And AGN are both intrinsically and extrinsically variable. There was a paper posted by Kazuo Akiyama and Michael Johnson of the CFA, or Michael is, that talked about this a little bit more recently. So it's a variable source. That's it. So we got follow-up imaging with the VLA and monitored it over the past few weeks, and we see variability that precisely has exact same characteristics of the claimed transient. In particular, we reach flux densities as high as they've seen, and we also see in our very last epoch from last night some rapid spectral variability. So this is just a variable radio source. Therefore, there's no reason to believe that there is a transient. Therefore, there's no reason to believe this has anything to do with the FRB. One thing I want to point out is people have argued that what they mentioned in their paper is that if you look at the dispersion measure of the FRB, the idea is that it's going through the IGM, and so given what we know about cosmology, you can sort of estimate a redshift of a host, assuming a cosmological interpretation. And one thing that was pointed out was the redshift of this claimed host was consistent with what you'd infer from the dispersion measure. But a lot of redshifts are consistent with that. I did a simple Monte Carlo analysis of given the single measurement of the FRB dispersion measure and sort of the same model they use, what redshifts would be consistent. And anything between 0.4 and 0.65 is consistent at the 1 sigma level. And that's exactly, so the lower left here is kind of a cumulative distribution of AGN redshifts for 101 millijanskis. And, the sort of like 0.5 to 1 redshift is exactly what you see for your generic radio AGN. So the fact that these overlap is not very surprising. And that's it. There's also been other work where Vedantam et al., they also got a broadband spectrum of this source and showed that it's very flat, which is also something you expect from an AGN. So it looks like this source is just an AGN that's scintillating. It's very close to the galactic plane. It just happens they had some bad luck where, they saw 2 up and 3 down. And, we looked again, and it goes up again. That's it. Thank you. We haven't gotten a formal response. They've said that they are waiting for these work results to come out in the referee literature. This will probably be accepted today or tomorrow, so they can proceed to consider the evidence that we offer. I will say that I feel that this is something the peer review process, I'm not very idealistic about it, but I feel like the peer review process should have at least raised these questions. The paper should at least be forced to deal with them. And, I think something has gone wrong in this particular instance if that did happen. Thank you.
Okay, thanks for letting me speak. I wanted to introduce a project I've been working on for the past 3 months. It's a website that basically presents all of the observed supernova data in, I think, a fairly easy-to-use, user-friendly way. And if you so desire, it's okay to pull out your phone and go to this webpage right now, but you don't have to. But it's a very short URL. just SNE.space. And you can just Google open supernova catalog and it'll pop up as well. Very easy to find. Okay, so I'm going to tell you why I put this together, how I implemented it, how you can help. And I think this also shows maybe a nice path forward to making catalogs of other astro things of various sorts. Okay, so the beginnings of this, basically I study tidal disruption events. That's primarily what I do. A couple years ago, I thought it would be nice to have a table of tidal disruption events, so I just put together a very quick HTML table that looked vaguely like this 6 months ago. It was very modest, 60-ish entries in the table. And so, I didn't have really big aspirations for it at first. But then, it occurred to us that when LSST comes online and other wide all-sky surveys come online, that this number could grow a lot. And it would be nice to have a good catalog of these things for people to use as a tool. So I approached Jared Parent here, who you might remember gave a talk at the ITC Luncheon maybe 7 or 8 months ago, because he seemed to know a thing or two about how catalogs work. And really my idea was just to copy the best that the supernova people had done, because that was a fairly well-established transient community. And I thought, hey, we can just copy what they're doing, and maybe we can make something nice out of that. So in long discussions with Jared, it turned out that copying what is currently being done for the existing supernova catalogs is maybe not the best idea, because they have a number of flaws. So this just leads us to points for what I think makes a useful astronomy catalog. Firstly is completeness. Does it have everything? And that's something that is sort of the bare minimum for a catalog. Does it actually include everything that's considered a supernova? Is it up to date? Does it actually have the latest supernovae, the things that have been discovered in the past several days or so? Is it accurate? Right? Can we actually trust the data on the table? That's somewhat important. Where does the data come from? In a lot of these tables, you have no idea. Someone puts a redshift on a supernova. Who measured that redshift? What spectrum was that? No idea from reading these tables. If there is an error, how do you actually go about fixing that? How do you actually follow the corrections if that occurs? How do I know that actually an error has been corrected in a given supernova? Is the table accessible? Can I browse it quickly? Can I actually find data that I want to find very short time scale? And is it easy for me to actually pull it into scripts that I might be writing as a scientist to do data analysis on these events? So for the supernova community, there's a number of catalogs that do various things. There's the Asiago catalog, which is a big table of metadata, mostly pre-2015 supernovae. No photometry or spectra on that catalog, just metadata. WISEREP and the Transient Name Server, which is brand new. They have a very large collection of spectra, about 10,000 plus. Very far from complete. It's very inaccessible as well. If you want to download spectra from multiple supernovae simultaneously, it can be very difficult to do that. You'd have to go through them one by one. There's also a very nice photometry catalog put together by ITEP at the Sternberg Astrophysical Institute. It's a very large table. It's the largest collection of photometry on the web currently, but it's all HTML tables, and each event is on a single page. So it's also extremely inaccessible. The individual groups have their data, and if they're nice, they give you a data dump, right? They put all their data on their web page, and you can pull from that. But it's just the group's particular data, right? If you're at the CFA web page, you're not finding Berkeley data on that web page. And some of the groups just don't bother making any of their data public. They'll be in publications, maybe one event at a time, but they won't make any big data dumps, or they haven't done so for 5 years. So that's a bit of a problem, and it's very inaccessible. It's hard to find the data you want in a supernova. Lastly, I just want to point out Wikipedia, right? Like Wikipedia is how you would learn, you just type in something in Google, name of a supernova, that's probably the first thing that actually comes up. Wikipedia is very accessible, right? The data is immediately there. It's extraordinarily inaccurate, though, right? It's just random people editing this, and there's no accountability. It's very hard to navigate that. So I think we're all paid by public money here, whether it's dollars or euros or yuan, and we can do a lot better than this. And so this is our attempt to do that. So the idea is that observers publish their data in papers. They will oftentimes be nice enough to share that in machine-readable form, say an ASCII table. We think that probably the best way of sharing your data is using a service called Vizier, which most of you should be familiar with. Unfortunately, people don't use that as much as they should. What the actual script we've done does is it just goes through a whole laundry list of sources, web pages, individual publications, online transient catalogs, and it converts that to a standard file format, this JSON file format, which is just basically JavaScript. It's very simple. I'll show you in a moment. And in the end, we've compiled a huge folder of JSON files, one per event. Each of those JSON files contains every bit of data for that supernova, all photometry and spectra that's been publicly released. Parsing through those files to make a catalog, that catalog feeds a web page. That web page is then rapidly searchable. And everything we've done here is open source. It's all on GitHub. So if you want to actually duplicate it to do something different, or you want to change the way the script runs a little bit, you can actually go through GitHub and contribute. Okay, so very briefly on Vizier. Why Vizier? It's an established service. It's been around for a very long time. It makes the data very predictable. I know that when I query Vizier, the data is going to come out in a certain way. It's tagged. I can actually import that very simply. And to just give you a sense of how much work is involved in writing a script that parses a Vizier source, here's 3 snippets of code that pull data from Vizier, an ASCII file, and from an HTML table. And you can just see just all the additional work that's required to parse data that's in an HTML table, just because that HTML table is very unpredictable. Exactly where the data is in the web page. It takes a long time to actually figure this out. So when you put it on Vizier, it makes it so much simpler for people who want to use your data to pull from it. And it's not just for us, it's for anyone who wants to use your data. Okay, so now we're going to do a website demo. So this is basically what it looks like. Oops. Make it bigger. So on the surface, it's very simple. It's just a table, right? So it's a table of supernovae. You can sort it in various ways by clicking on these headers, by the amount of photometry, by the amount of spectra, RA and DEC. You can search for things very simply. So if I type in Tycho, you'll pull up Tycho in this table. Basically, we've tried to make this as slick and as fast as possible. You'll notice that I'm not connected to the internet here. So this is actually working because it's downloaded it all into your browser, and it uses your local CPU to actually do computations on the catalog. And you can do things like, say, I want to find all the supernovae with redshifts less than 100th. Let's do 1A supernovae. Let's select all these guys and export that to a comma delimited file. And this file now contains all of the metadata for all the 1A supernovae that are less than that redshift I've chosen. So this is extraordinarily fast. It allows you to do really, really rapid evaluation of the supernova data. If you actually click on one of these event names, this is just to show you this is what it looks like on a phone. So you actually can use it on a phone, and this sounds silly, but nowadays, when you're just kind of casually talking about a supernova, what's its RA and DEC, you can actually go to the website and pull that up immediately. An individual event page looks like this. We have the photometry, all the photometry and spectra that have been collected here for 87A. You can hover over individual points in the photometry and in the spectra, see information on them, see what refereed sources they come from, a big list of sources for where all that data comes from, metadata, host image if it's available. 87A doesn't really have a host image, obviously. And it actually allows you to find interesting things. So with 87A, we noticed that when we pulled the photometry from 2 different sources, that in I band, which is the same color in this plot, there's 2 different light curves, 2 different distinct light curves. And so this is all on GitHub. So this is a source code thing. And we made an issue for it. We said SNA, or supernova 87A, there's a photometry mismatch. What's causing it? And so Jared and I figured it out. There was, in one of the papers, claimed 0.3 magnitude difference due to some emission line issue with the photometry from one of the photometry sets. So this is a system where we actually could figure out what was wrong and fix it. Okay, so I'll very quickly go through this. So this is just statistics of types of supernovae. You'll notice about 45% of supernovae are untyped. And then if I go down here and I say which supernovae actually have public data available, 75% have no spectrum or no light curve publicly available. So that means that even though 55% of supernovae have been classified, there's a large fraction of supernovae for which the actual data by which they were classified is not easy to find. So that's a big problem, I think. We have a to-do list. These are all the things we want to add to the catalog. If you want to contribute, this is the way to do it right now. Basically, add your paper to this list. And on the main webpage is a link to this. Lastly, you can do cool things with the full data set. So this is just every single photometric point from 1A supernovae, all of them. And it's a big mess, right? So of course, when you do the stretch and that kind of thing, you can make this all in a nice sequence. But this is actually really great for finding outliers, for finding things that are maybe a little bit different than your typical 1A. This is 50 lines of Python once you actually have access to the full catalog. Supernova positions, just something very simple. Okay, so the last thing I just want to finish off with is the idea here is that this kind of thing that we've put together, relatively easy, simple. If you have a catalog of stuff that you want to put together and make user-friendly and accessible, you can use software very similar to what we've put together and make a catalog like this. And so we just collected together a few project ideas. Some of them are barely developed at all for doing these open kinds of catalogs. But the idea is that this is actually a publicly friendly face for the astronomical data that we've been collecting over the years. So thank you. What's that? Yeah, so I should mention that one of the main reasons why we did this is that Hanno Rein, I don't have the internet right now, but this is a very nice exoplanet catalog that he put together. It's very similar. It's all on GitHub. You can download everything that you want from that catalog. My philosophy there, putting links here, is that you don't have to use my software. So long as the data is open and you can download everything, you can be on this page. So it's really just an idea. These are the catalogs that have, in my opinion, done the right thing.
Thank you from the community. This is a fantastic resource. So my question to you is, having used Vizier a lot, I actually find that, it's not that infrequent that there are mistakes. Like you're looking at one object, and actually they're giving you the information for another one.
Right,
things like that. I don't know how they happen, but they do happen. So can I ask you, do you have cautions where you would say to the community, be careful using it for certain types of projects?
Most definitely. Like, you're not going to do 1A cosmology by using the mess of 1A light curves that I showed in the previous plot, right? Like any kind of precision type thing, this is not exactly the right tool to be doing that unless you're very, very careful. One thing we did try to do is that on an individual event page, you'll notice that sometimes there are quantities that are reported slightly differently in different sources. So for RA and DEC for 87A, if you look at different pieces of literature, very slightly different values for those, but 87A is a good example for something where most everything agrees between the sources. Sometimes you find different redshifts from different sources, and so there's a lot of cross-checking here. You can actually see like who said what. And so that's a way that you can actually identify potential mistakes in the catalogs.
Thank you very much. So I'm going to tell you about a work I've been finishing with my student Stephen Pardee, the University of Wisconsin-Madison. So it's about an interesting features of some class of galaxies called Magellanic irregular galaxies. And it is, so this class of galaxies are very peculiar because they do show one arm. Most of them shows actually a bar, but the bar is also offset with respect to the photometric center of the disk. And they have been, measured and observed initially from the Bouwens and Freeman, and they're still a puzzle class of objects. Also, sometimes they are found around massive spirals, but the majority are not found around massive spirals, except the Large Magellanic Cloud, which is around the Milky Way. And also most of them don't seem to have a visible companion. Again, except the Large Magellanic Cloud, which is a prototype, and it has a companion, which is the Small Magellanic Cloud. So I got very intrigued by this class of systems. And just to mention the LMC, as you can see here, this is an optical image of the Large Magellanic Cloud. So from this recent work from Van Mar et al., 2014, you can see how messy is these systems. So it has actually, there's no determined center. There are at least 3 centers in the Large Magellanic Cloud, a center in the bar. Then, this bar is offset with respect to the H1 center for the gaseous disk. And then if you measure the outer disk, so the center from the outer disk, as you can see here, it's very messy, the Large Magellanic Cloud. It's also offset with respect to the bar and the H1. So the center of the LMC is not very well determined. And this is the prototype of a Magellanic spiral. So I would say that, according to the definition or initial observations of Freeman and de Vaucouleurs, it is an offset bar. So this is another case in the field, that's NGC 3909. You can see that if you look at the optical disk and then you look at the bar, it seems again very shifted. It doesn't have a companion, at least not a visible, obvious companion, and it's in a little group actually. And so from a survey from Wilcox et al. Of 10 years ago, more or less, so they look at in H1, these Magellanic type galaxies, especially the one in isolation, and they saw that there are only out of 13 have some interferences or some disturbances due to the presence of a companion. So there's no an obvious interaction. But we know that the prototype, like the Large Magellanic Cloud, had a flyby with the Small Magellanic Cloud recently. So the prototype had actually some interaction. And it's an interesting interaction because it's an example of an interactions between a dwarf galaxy. So what we've been doing here is trying to answer the question. So what is the nature of this offset bar? So why a bar at a certain point, which is, an axisymmetric feature of a disk, gets offset? And is there a real offset? And also, because the LMC is the prototype, and we know that it had an interaction with a Small Magellanic Cloud, we want to see with simulations using hydrodynamics and embodied simulations how we can generate these features like one arm, the lopsidedness of the disk, by interactions between the Large Magellanic Cloud and the Small Magellanic Cloud. And can we reproduce this offset bar, or understanding the nature of the offset bar? Also, how long-lived are these features? Do they recenter? Is the bar is really offset? Does it recenter in how long? So what we did was to simulate a Large Magellanic Cloud in interaction with a Small Magellanic Cloud-sized galaxies without assuming the potential of the Milky Way at this point. And here you can see, so in the simulation, so here is the stellar disk, and this is the gaseous disk of the Large Magellanic Cloud as a function of time. So here is at the time where the companion, the Small Magellanic Cloud, has been introduced in the simulation. That's the time when it hits the disk, and then that's the evolution after that. So this is surface density plot, and here you can see these ellipses are the isocontour density, like the observers would do, to the Magellanic system. And here we have initially we start with the bar. And then we look at what happens to the bar after the interaction with the Small Magellanic Cloud. And that's for the gas and that's for the stars. So the inner ellipse here matches the bar. And the outer ellipse, the solid black outer ellipse matches the outer disk. So as you can see, after the interaction, actually the stellar disk becomes very messy. And so very asymmetric. And so the ellipses don't have the same center anymore because the outer disk becomes very asymmetric. So the first thing we learned is strong asymmetries in the outer disk. Now let me show you a movie that shows what happens. So we measured actually the offset between the stars in the disk, which are the red lines, and the center and the center of the bar with respect to the dynamical center. So here we measured all the centers, the center of the bar, the dynamical center, and actually we measured also the center of the disk using the ellipsis like an observer. And as you can see, as a function of time, the bar never shifts. So the bar is always centered at the dynamical center. But the disk, because it becomes so asymmetric in the other parts, so it doesn't have a photometric center that coincides with the bar. So it's not actually a bar which is offset, but it's the disk which is dislodged, or let's say offset. So the first thing we learned is that the bar always coincides with the dynamical center, and the disk gets very lopsided and appears very dislodged. Also, we did it with different configuration, different kind of orbits, different kind of interactions between the Large Magellanic Cloud and Small Magellanic Cloud, but again, we find always the same result. The bar is always centered. We also look at different profiles for the dark matter halos. We know that many dwarfs seem to have a chord halo profile instead of a cusp. So we see that in the case of the cores, with the different configurations in the orbits, we see that there's slightly more misalignment between in the offset, but again, the behavior is again very similar. And as you can see, the offset could be up to 2 kiloparsec. Maybe the LMC is around 1 kiloparsec. Now, what about the H1 gas? Does it get off-centered as well? And the answer is actually yes. Even the gas gets a little bit dislodged, but the gas dissipates, so it recenters actually quicker. And so we look at also some, we use some packages like DiskFit to determine the H1 center. And we saw that actually it will recenter very quickly. So what I think it's interesting, this work, is not only to understand, the nature of this offset bar that don't seem to be offset, but it's just the disk that gets offset when it is in interaction with a massive companion. But it's also because if you apply all these analysis to the Large Magellanic Cloud, I think it becomes clear that the center of the Large Magellanic Cloud should be chosen where the bar is, if we believe this work. Whereas up to now, it has always been chosen on the H1. Now the H1 gets most of the time actually the H1 disks are symmetric, so it makes sense to choose, but in the case of the LMC, because it is part of this class of objects, I think it's a better choice probably to choose the bar as a center of the LMC. And if you do this, then you will see that the proper motion, the north component of the proper motion that depends on where you center the Large Magellanic Cloud changes, they increase, slightly increase. So what's the effect? The effect is that, if we go back to the values of a few years ago, actually the north component of the Large Magellanic Cloud, that means that because the north component of the proper motion actually regulates the projection on the sky of the orbit of the Large Magellanic Cloud, it gives still a misalignment with the Magellanic Stream. So it would go in a worse misalignment between the stream and the projection on the sky of the Large Magellanic Cloud. Also, why I think it's interesting, because if you search for black hole for the Large Magellanic Cloud, maybe a good choice would be to look at around the center of the bar, because this seems to be the dynamical center of the cloud. I think I'll stop here.
I remember from a few years ago, there was a claim that the H1 in the LMC was affected by ram pressure on one side. Is that still the case?
Probably, yes. I think there is some interaction. Yeah, there is some ram pressure going on, but doesn't affect actually the center.
But your analysis wouldn't include the effect of ram pressure?
No, my analysis is just telling you that the bar never offset. So there's no offset bar in the Large Magellanic Cloud. There's no offset bar in any Magellanic spiral galaxy. The bar is always at the center. Disks get dislodged. And I would say you're expecting the same even in larger galaxies, but it's so unlikely to have a galaxy which is a factor of 10 less massive punching the disk of the Milky Way, so you don't see it. But in this kind of galaxies, because the LMCs may be a factor of 10 less massive than the Large Magellanic Cloud, then you see this effect.
LMC interaction?
Not from the offset, but the time scale is an interesting question because it takes, actually it takes 2 gigayears to recenter. So it's a long time. So for the LMC, this tells us that maybe because the H1 is much faster in recentering, so the H1 is still off center right now, but it will recenter in a few million years. But the stellar disk will take longer because the collision happened only 200 million years ago between the SMC and LMC. Thank you very much.
Okay. Let's see. Just this is the laser pointer. Okay, so it's a pleasure to be here. So I'm going to be talking to you about spectroscopy. So many of you, I'm sure, have gotten used to hearing all sorts of pundits of the high redshift universe claiming to find all sorts of very distant objects in the faraway universe. And the question you might ask yourself is, are all these objects really so distant? Are they really as far away as we claim? And to try to address this, it's useful to get spectroscopic redshifts or spectroscopic confirmation. So why spectroscopic confirmation? So spectroscopic confirmation is really useful for testing the integrity of these large samples of objects that we identify in the distant universe. And we generally identify these objects by taking advantage of large photometric surveys and the fact that there's the huge amounts of neutral hydrogen in the distant universe essentially impose a very strong break or feature in the spectrum that, when viewed through a bunch of broadband filters shown here, you can essentially see as disappearing at the bluest wavelengths and showing up quite prominently at the reddest wavelengths. And so spectroscopy really allows us to test whether sources found in this way are really at the redshifts that we claim that they are. It also allows for the physical study of sources, because once we know the redshift of a source, for example, of a redshift 6 source, we know where all the other lines are, and so we'll know where to, for example, look for, say, a 2.5 or 3 sigma line is in the spectrum of, say, a redshift 6 object. So this can tell you just things about the ionized nebula. It can also, in the case of this redshift 5.5 source, allow us to study with ALMA. You really require precise redshifts for study with ALMA, for studying specific lines, so you can learn about the dynamics as well. And finally, spectroscopic redshifts are great for breaking records, which is always fun to do as well and get in the media. So what tool do people typically use to get redshifts? Well, effectively, a workhorse tool has always been the Lyman-alpha emission line. It's a very, very strong emission line that you can see in large numbers of these different distant objects, and it occurs at a wavelength where we have spectrographs that allow us to readily find this line. Now, the challenge with using this line to find the most distant sources is illustrated with this diagram here, where you show the fraction of galaxies showing Lyman-alpha emission versus redshift. And so what you can see is that about 40 to 50% of objects at high redshift, around redshift 4 to 6, show Lyman-alpha emission quite prominently. These things are selected photometrically. But once you go beyond a redshift of 6, a lot of the candidates stop showing Lyman-alpha emission. It becomes increasingly less prevalent. That is thought to be due to the fact that as you go back to earlier and earlier times, there's more neutral hydrogen in the universe, and the neutral hydrogen is basically the Lyman-alpha photons are resonantly scattering off the neutral hydrogen. And that's basically causing, as you go back to earlier times, for this Lyman-alpha emission line to effectively disappear. So how might we hope to find Lyman-alpha emission despite all of these things? Well, despite these challenges? Well, it's still a strong line, so let's go out and try to find it still. But one good thing to try to do is look at the brightest galaxies. Brightest galaxies are obviously very useful to do because they have very high signal to noise. Bright galaxies are also very useful because it's easier for Lyman-alpha photons to escape from them. Because for a very bright galaxy, you have a massive potential well, you have higher velocity inflows and outflows, and essentially this introduces larger Doppler shifts in scattered light Lyman-alpha photons, which allows the Lyman-alpha photons to get out. And number two, so first look at bright galaxies. What's another good thing a principle to keep in mind in trying to find these Lyman-alpha emission lines? Look for galaxies which are dominated by nebular line emission. And I'm going to suggest to you can detect this, determine which objects are dominated by this line emission from the photometry. And so if you have lots and lots of line emission or ionized gas, you're much more likely to find Lyman-alpha. So how can we finding bright sources, that's pretty obvious how you do that. How do you go out and find line-dominated sources? Well, here I'm just showing you the photometry that you would have. These are photometric observations that correspond to some model SED. Here's a star-forming galaxy, flux versus wavelength, some model SED, and here's a Lyman break, here's photometric observations with HST and with Spitzer. And this is for a source which doesn't have much line emission. Now let me just add some line emission to this source. So add more line emission, and what do you see happen? Well, you can see that, you're going to get more Lyman-alpha, for example, but you're also going to get huge emission lines at various other wavelengths, and in particular, there's a very strong O3 line and H-beta line here, which adds huge amounts of flux to this reddest Spitzer band. So basically, this one gets contributed a little bit, but this one gets contributed to a lot. So you just look at this, you basically get these very, very red colors. And from these red colors, you can infer that this source has a lot of line emission. So now that we have a search strategy, let's see if we can actually find sources that show lots of Lyman-alpha emission. And so let's go out and try to find them. Where are we going to look? Let's look at candles. It has 2.5 months of HST time. Here are lots of the different survey fields. Approximately covers the full moon. So lots of time. And so could we find some sources? And the answer is yes. We found large numbers. Here's an example of a source. Basically has the same profile as what I showed you before. Very, very red Spitzer colors. The photometric redshift was around almost redshift 8. And we didn't just find one, we actually found 4 very bright sources over the candles program. This was in a paper led by a student of mine in Leiden, Guido Roberts Bersani, for basically a master's project. And basically he found 4 objects, here's the images, with Spitzer, which show these very red colors and which were very bright. Now's where the rubber meets the road. Do these things actually show can we get redshifts? Do these actually show Lyman-alpha emission? So we use Keck, and so what are the results? Okay, so here's one of the first sources we looked at. Basically was reported in this paper from last year. This is a 4.5 sigma line. This has been subsequently confirmed at more than 10 sigma by an independent observation of this line. This is basically Lyman-alpha suggests at redshift 7.48. Here's yet another source in the sample. This is a 7.73 object, was a record breaker, broke the highest redshift record at the time. This was led in a paper by Pascal Oesch, who actually took the observations at Keck. This is Lyman-alpha. Here's the two-dimensional spectrum of Lyman-alpha. This happened last year. 2 months later, this is the observations of the same 4-object sample. Basically, we asked Adi Zitrin, who's at Caltech, to go out and to look at another source from our sample, and lo and behold, they found Lyman-alpha in this source, redshift 8.68. Again, broke the record. Lots of headlines in August and September. And so, at present, all the sources have been followed up. We know from some collaborators that this source has a redshift of 7.15. This is the 4th source that I didn't talk about. So all 4 sources show Lyman-alpha emission. They broke the record twice, high redshift record twice. And so we had 100% success rate in following of Lyman-alpha, which is quite a bit better than what people were finding. Quite a bit better than what people were finding prior to this sort of study, where they were getting about essentially a 0% success rate. And so with the redshifts in hand, we're now trying to characterize the physical properties of these sources. So with redshifts in hand, we're now trying to actually study them in more detail. Of course, we've recently been lucky, as we've taken some other observations which have allowed us to get redshifts. Our team has, so we can also measure these redshifts from the position of Lyman break. This is just a little addendum to the talk, and one can also try to directly observe the Lyman break from basically GRISM observations with HST. This required basically a full day of observations. It's very expensive. This is much more expensive than trying to find Lyman-alpha. However, if you push really hard and use lots of HST time, you should be able to confirm a lot of these sources. And this is effectively a prelude to what will be able to be done with JWST. So this is my summary. Spectroscopic redshifts are valuable. Verifying nature, physical characterization, breaking records, and the recipe for finding things with strong Lyman-alpha emission are basically finding bright, massive galaxies, and galaxies which, according to their photometry, appear to be dominated by nebular emission. And also, if you spend a lot of time, you can get spectroscopic redshifts using continuum breaks. Okay, so thanks. It's a pleasure to be here and take some questions. Oh.
One reason you might have been successful, in addition to the Doppler effect that you mentioned, those bright galaxies also often reside in overdense regions in the universe where the H2 bubbles during ionization are starting. So it's more likely to find a region that is ionized in the vicinity of the massive galaxies. So that could have helped.
Yeah, that's another bonus to using the bright sources. You're right. Yeah.
I think you're selling ALMA short. You can actually do a redshift search with ALMA by observing only 2 bands, and as ALMA really comes online, that's going to become easier and easier.
Which bands are you proposing? And you're looking for C2 or another?
Well, there's the various CO lines, there's the carbon lines, there's the carbon 2 line, nitrogen 2 line, oxygen line. And so by choosing 2 bands in ALMA and observing those 2 bands, you're definitely going to get at least 2 of those lines mentioned. And so it's not unreasonable to do a redshift search with ALMA.
Well, yeah, that should be fun, particularly as it transitions to full ALMA rather than 60% or 70% ALMA.
Any other questions? I guess you made a very strong case.
Okay, right, yeah, everyone's convinced.
Assisting us with more discoveries.
Okay, thanks.
Are you here for a couple of days now?
I'm here for a few days.
Well, it's very good that I followed that paper because I want to take us back about 150 years and talk about the beginning of spectroscopy that is going to turn into astrophysics and look at how this started in the United States and try to persuade you that there was a very important connection between instrument making in the United States and early astrophysics in studying of the sun. And the 2 key players here are Alvan Clark, who I presume you know, and you can tell from the grating here, Henry Rowland. And I'm going to tell a story from about 15 years about an instrument that was developed by Clark that is going to be made completely obsolete when the grating comes in. Okay, so 1860 is when Kirchhoff puts together the idea that there are emission lines and absorption lines, and realizes this has something to do with chemistry, right? So there have been the lines in the sun, going back to Fraunhofer, the dark lines, for 50 years. People didn't know quite what there were. There were wonderful theories about what those lines might mean. Kirchhoff is going to say, okay, 1860, it has to do with chemistry. And so that then is going to, that's sort of the date that I picked for the beginning of astrophysics. Suddenly you have a new tool, and you can start to think about this light coming from away in new ways. But the big thing you need to do is to try to increase the dispersion so you can see more lines. So Kirchhoff himself is one of the first persons who brings together more prisms to increase the dispersion in the spectra that he gets. And this is going to, of course, work for the sun because in each of these optical surfaces you lose intensity, right? And so you have a small source that's not going to be able to get through that many prisms, but with the sun you can. So the early 60s, 1860s, the question is how can you study the sun and how can you see more lines in the sun? And European instrument makers follow up on Kirchhoff and say, okay, can we simply make big trains of prisms to get more and more dispersion as you go through? So here's one that's actually mounted on a telescope. And London makers start to simply pile up prisms. Again, you try to put a light that you're producing in the laboratory through this many prisms, and you're not going to have enough intensity to see anything at the other end. But with the sun, you can. Well, if the prisms are fixed, you're only able to look at one narrow part of the spectrum. And so already by 1863, here's where Clark first enters the story. And he works with somebody named Cook. And this is now my test for how much you know Harvard history. Does anybody know who Cook was in 1863? He's a Harvard professor, but not in physics or astronomy. He's a chemist. Josiah Cook. And he was the first person at Harvard to study microscopy, and also wanted to, or spectroscopy, and also wanted to try to get increased dispersion. So what they did was develop together, working with Clark, who was the instrument maker down in Boston. He might be in Cambridgeport already by this time, where you put a train of prisms together, and you have a steel band that can either pull this, that can affect this radius, and therefore you can change the angle of the incoming light, and you can sweep through the spectrum that way, and you can look at various lines rather than just being fixed at one line. Well, this is picked up in Europe, and you get the same kind of thing, and increasingly you get these Rube Goldberg kind of ways to arrange this so you can smoothly sweep through the spectrum. It gets even crazier. Here's Rutherford, who's an amateur from New York, figured out a way to use sort of slotted mechanisms to move his prisms. Here's Browning, the London maker, again, is doing the same kind of thing by 1870. So this first 10 years, instrument makers are trying to build devices that let you increase the dispersion. Browning in London, we're not quite sure about the date as to whether he's before or after Clark on this, invented what we call the two-story or the double pass, where you take the light through one set of prisms, and then you flip it up with 45-degree prisms, and you send it through again. So you have 6 prisms, you can actually send the light through it 12 times, and of course, you're increasing the dispersion all the time. This is an extant spectroscope that is in London at the Science Museum. And it gets even crazier. This one was never built, but this is the equivalent of 36 prisms that the light was supposed to go through this way, and then it would come back and go through the other way. Again, think what the role in grating is going to do. This one wasn't built. Okay, to come back to the story of astrophysics. So 1869 is the important year for both Harvard and for Dartmouth. Now, I don't want to get into a chauvinistic question about who did what first, but this talk is going to sort of be that way. So I will apologize in advance. Since I've been at both institutions, I guess I can tell stories on both sides. Anyway, so in 1869, the astronomers here decide that they want to look at the sun, and so they order the prisms, 5 prisms, from Steinheil, who's the best optician in Munich. And they don't trust Clark to build his spectroscope, so they're going to send these to London to be mounted by Browning. And something happens, it gets slowed down, and so they finally say, okay, just send us the prisms. And they go to Clark, and so Clark designs then this fixed mount system. So this can only look at one line. They wanted to study prominences. I think it was the F line they were looking at. He designed this with fixed prisms. It went into the observatory, and as far as I can tell, there was no published data that came from this. They had the instrument, but the director at that point, this is before you get to Pickering, was sort of doing administrative things, and he did not actually start studying the sun with this. Well, this takes us now up to Dartmouth and Charles Young. Charles Young was a student at Dartmouth in the 50s. Then he went and was teaching in Ohio, and in 1866, Dartmouth brought him back to be the professor of natural philosophy. And the first thing he did in 1866 was to order from Clark a spectroscope. Didn't get the glass now from Steinheil, got the glass. Clark made the prisms, heavy flint glass prisms. And this is in a book. This shows the early arrangement here. He did not have the mounted that you could put on a telescope, so he was simply learning about spectroscopy. But in 69 was going to be a solar eclipse, a total eclipse that was coming across the central part of the United States. And Young decided to build what he called a prism box. So he built his own box, taking 5 of those prisms to get the dispersion, and went out, and this is the photograph from Burlington, Iowa, and this is the Dartmouth telescope there, and you can't see the prism box at the bottom. But anyway, with this, he was able to see a line. So he was studying the corona during the total eclipse, and he saw a line in the green that was completely unknown, and that was the important discovery of this 1869. There had been 1 or 2 eclipses before when you started to do spectroscopy. This was one of the most important ones. This line did not match any lines in the known spectrum. Young thought it might be iron, but he was very unclear, and he sort of changed his mind on this. And then by the 1880s, people thought it was a new element, and they called it coronium. This is an element that's just in the corona. It's in the green. And for the next 40 years, people explored this element. So discovered in 69. It's not until 1939 that people realized it's simply very highly ionized iron. It's iron 14. And that was the first evidence that the corona was really hot, like 1,000,000 degrees hot, to produce that kind of ionization. So that's a very important discovery that came from those Clark prisms. But then Clark and Young sat down and said, okay, let's do this London idea. Let's do a double pass. So we have our prisms here, and we'll send the light through them twice. They added photographic units. You could take pictures of this. And this is what it looks like on our telescope. It's this big, heavy chunk of glass hanging down at the bottom of this. He used it first in the September of 70 to take the first photograph of a solar prominence. And I'll show you this a bit when we look at the actual instrument, how they did this. He had to decrease the intensity of the light and was actually able to hook up a camera and do a 3-minute exposure during the, on the limb, and they could actually take a photograph through this device of the prominence. So this is, but then he took it to Spain in 1870, and another total eclipse, and that's where he saw the flash spectrum for the first time, where you get the just at the time of the totality, you get the shift from the emission lines to the absorption lines to the emission lines. It lasts about 2 seconds, and it comes back. And he saw that, which showed that the layer of the atmosphere of the sun that was making the absorption lines was very narrow, very close to the surface. This is what the device looks like. We still have it in our collection. So here is the chain of the 6 prisms that goes through once, and then it flips back. Here's the mount onto the telescope. And then here is this interesting device that you hook this up to a motor and you spin this, and that moves the shutter back and forth, and you can decrease then the intensity of the light. This is how that works. We won't go into the details. That's how he took the photograph of the prominences. Well, with those 2 discoveries in 69 and 70, that sort of put Young on the map. That put Clark on the map as being this good optician, and Clark made 2 additional multi-prism complicated spectrographs. But then by 1879, Rowland starts having his grating, and Young never made another multi-prism spectroscope after that. In other words, the grating came in already in 1873. Young wrote he put a grating in his spectroscope. The grating is much lighter and easier to manage than a train of prisms. If similarly ruled plates can be made at a reasonable price and quality, it would seem obvious that for solar observations, they might well supersede prisms. And that's exactly what happened. That complicated Rube Goldberg device of all those prisms went away. You weren't hanging those on telescopes anymore, and people were using single gratings. Well, then in 1881, Young writes this book, The Sun. Some people might claim this is the first book of astrophysics published in the United States. It's actually a semi-popular book. Doesn't have a lot of math in it, but nonetheless, it's a very nice summary of sort of the first 20 years of studying the sun after Kirchhoff and Bunsen, and became the beginning, I think, of American astrophysics. Now, in terms of Dartmouth, Harvard, I have to say in the end that, of course, what did Young want? He wanted a bigger telescope. Dartmouth said, no, we don't have enough money to build you a bigger telescope. Princeton said, we have some money to build you a bigger telescope. He went to Princeton, and that's where he trained the first generation of American astrophysicists, including H.R. Russell, for example, of the HR diagram, was a student of Young. Thank you. And Young he got his new 24-inch telescope, and he made no discoveries of any importance when he went down to Princeton. So maybe that explains why it did become theoretical.
You mentioned what sort of spectral resolving power resulted from the stacking of prisms.
As to what the total dispersion was? Oh gosh, I don't remember what it was, but it was big. They could see a lot of lines by sweeping through with that many prisms. But you could only do this on the sun, right? You needed to have that tremendous intensity to get through all those optical surfaces. Thank you. There you go. Thank you very much.
Thanks.